Hello, this is day 9 of our daily push-up challenge while doing a Putnam problem. This particular Putnam problem comes from 1998. We'll read it after the first 5. 1, 2, 3, 4, 5. And again, just like yesterday, we write it on the upper right so that we won't forget. So the problem reads, given a point AB with B greater than 0, A greater than B, determine the minimum parameter of a triangle with one vertex at AB, one on the x-axis and one on the line y equals x. 6, 7, 8, 9, 10, and we write it here. Okay, so let's draw the configuration. This is that's an ugly x-axis. There is our x-axis, and this is our y equals x diagonal. Okay, so we have a condition that A must be greater than B. So in other words, we will only be considering this region right here because A is the x component because the point is AB. We will be choosing the point AB. A has to be greater than B. Therefore, all points that are in here, whereas on the upper side of the diagonal, they're not included. So let's just erase that. Okay. 11, 12, 13, 14, 15. Okay, so 15. All right. So we choose a point, any arbitrary point. So let's put it in red. Let's say I choose, I don't know, this point. Okay. So this is our point AB. So that's one vertex of the triangle. The other vertex must be on the x-axis. Okay. So we can choose it, I don't know, to be somewhere here, for example. Okay, so this one will have an arbitrary coordinate with y equals 0, of course, but it will have an arbitrary x value. The other one will be on the line y equals x, so somewhere right here. Okay, so these 2 points, this the one on the y equals x and the one on the x-axis, we've chosen that arbitrarily given AB, which again could be anywhere in the lower half of the line y equals x. Okay, so this triangle could be this one. Okay, so this is a triangle that we want. Let me fix that. Okay, the question is, we want to determine the minimum perimeter. Okay, but look, that could be given AB. We could have easily like defined some other triangle that looks like that. Okay, or we could have easily defined some other triangle that, I don't know, looks like this. Okay, right? So again, the problem is which of these points results to a minimum perimeter. But let's just have this our initial starting triangle, the red one, okay, and then continue from there. 16, 17, 18, 19, 20. Okay, let's write 20 here. So again, perimeter is just the sum of all the sides of the triangle. So what we can do is we can try unfolding our triangle. Okay, let's open the triangle. So for example, let's open it from the point AB, and then when I say we open it, we like detach that point, and then we attempt to make it into a straight line. Okay, so for example, let's take the reflection of AB along the x-axis. So let's say this point. Okay, so obviously this particular point will have a coordinate A minus B because it's the reflection. Okay, so basically what you did is you took this line and then you like move it this way. Okay, so that this line and this line have the same length. So why can't you can like move it anywhere else you want, but the nice thing about this particular point is you can relate it with the original AB. Okay, and of course we still want it to have the same length. You can't like take it like here or any place else, otherwise you won't be going anywhere. Let's do the same with the other line on top. Okay, this particular line, we unfold it such that we take this point, we take the reflection of AB along the y equals x line. So in fact, this particular point will now have a coordinate BA, okay? That's a property of y equals x, when the reflection of one point on the lower half of the diagonal AB will be BA, okay? So of course, obviously, this particular line will have the same length as this original red line right here. So we just move it in that direction. So therefore, the perimeter, which is given by the sum of the sides of the triangle, you could also be given by, so let me trace it with the blue line, by this one, okay? This particular path. This particular length will give you a perimeter of the triangle. So we're now at 20. Let's finish this. 21, 22, 23, 24, 25. Okay, so we're done with our push-up, but we're not yet done with our problem. How do we want a minimum perimeter? That means we want the blue line to be as small as possible given AB. Okay, so once you're given AB, this points right here, let me highlight it, BA and A negative B are already determined. Okay, the only thing that you can adjust are these points, the point on the x-axis and the point on the line y equals x. How do you make that minimum? Well, to make that minimum, since that line is tracing a path from B to point BA to point A minus B, this blue line that we drew, okay, note that the shortest path between 2 points is a straight line, correct? At least in Euclidean geometry. So in order for this blue line to be minimum, which is of course equal to the perimeter, we just connect, okay, we just connect the point BA to the point AB. Okay, so in particular, for the point AB that we have, in order to obtain the triangle with the smallest perimeter, you have to move this red point on the y equals x to this point right here, to the intersection of the straight line on the y equals x, and then on the x-axis, again, you move this point that we've chosen arbitrarily to this point. Okay, that way, this new triangle, which will be, let me draw it with a green one, this new triangle for the point AB, okay, should result to a smaller perimeter, and in fact, the smallest perimeter that you can have for that particular point AB. Okay, and so now it's just a problem of looking for the length of this this dashed blue line from BA to AB, and of course that's straightforward because we'll just be using the distance formula. So the distance, okay, from BA to A negative B is just given by the point x, which is x1, which is or x2, which is B, minus x1, which is A, the x value of the lower point. You take the square plus the y value of this point above, y2, which is A, minus the y value of the point below, which is negative B. So that's just plus B squared. And then we take the square root. Okay, so that should give you b squared minus 2ab plus a squared plus a squared plus 2ab plus b squared. Of course, you still have a square root there. This 2ab and minus 2ab will cancel. So finally, you get square root of 2a squared plus 2b squared. Okay, and that right there is our minimum perimeter. So given AB, given the location of AB, the minimum perimeter that you can obtain using when drawing a triangle using the given instruction on the question is square root of 2a squared plus 2b squared. Okay, so thanks for watching, guys. That's it for today. Day 9 of our Putnam challenge, and with a push up. Again, this is a Putnam problem from 1998. Thanks for watching. See you next time. Bye bye.